Welcome to Entropy and the Second Law of Thermodynamics. So entropy, which we symbolize with capital S, is a thermodynamic term that reflects the disorder or randomness of our system. So the more disordered or random our system is, the larger the value of S. So as we move from a solid, which is a highly ordered sort of structure, to a liquid, which is a less ordered structure, but we still have all of our molecules together, to a gas, which is a highly disordered structure. As we move to the right here, as we move from solid to liquid, liquid to gas, we're increasing the entropy. Now, the entropy increase from solid to liquid is smaller than the entropy increase from liquid to gas. As we go from liquid to gas, we are drastically increasing the entropy of our system. So, entropy is a state function. Now, a state function is a property that depends only on the current state of the system and not on how the system acquired that state. Which means a state function is independent of the path, as opposed to a path function, which does depend on the path taken to the system's current state. So a path function is something like the heat absorbed by the system during a process, or the work done on a system during a process. These things are not state functions, these are path functions. It depends on how you're getting from one state to another. But other properties like temperature, mass, these things are state functions. It only depends on where you are now. The energy of a system only depends on the current and final energies, right? The change in energy, you have some amount of energy here, some amount of energy there. It doesn't matter how you get from here to there, the change in energy is the same. Now, you have two different ways of exchanging energy, either as work or as heat. Those are path functions. So, for some system, the change in entropy, delta S, is equal to the final entropy minus the initial entropy. Right? And this sort of equation can be written for any state function. The change in state function is equal to the final value of the state function minus the initial value of the state function. So, if the change in entropy, delta S, is greater than 0, that means if it's positive, then the randomness is increasing. In order to get delta S positive, then the final entropy has to be larger than the initial entropy, and that means that our randomness is increasing. Our entropy is going up. If the delta S is negative, if it's less than 0, then the order is increasing. The disorder is decreasing. So suppose a system changes reversibly between state 1 and state 2. In that case, then we can say that delta S is equal to Q reversible over T. This subscript ReV means reversible. That means that Q, that heat absorbed by the system, is being restricted to a reversible process. So, let's look at an example of this. So, a phase change occurs at constant temperature with the reversible addition of heat. So we have solid water, ice. We add heat to it, and we get liquid water out. The second law of thermodynamics says that in any spontaneous process, the entropy of the universe increases. And this explains why spontaneous processes have a direction. Because in any spontaneous process, the entropy of the universe, not necessarily of the system, but the entropy of the universe increases. So, the change in entropy of our universe, then, is the sum of the change in entropy of our system and the change in entropy of our surroundings. So, change in entropy of the universe is equal to change in entropy of our system plus change in entropy of our surroundings. So, we can decrease the entropy of our system as long as the entropy of the surroundings goes up by more than the decrease in our entropy of the system, because delta S for the universe is always positive. So, for a reversible process, delta S of the universe equals delta S of our system plus delta S of our surroundings, which equals 0. So, for a reversible process, the entropy of the universe doesn't change. The entropy of our system or surroundings may change, but the entropy of the universe does not change. But again, this requires our system to be at equilibrium. For a spontaneous process, which means an irreversible change, the entropy change of the universe is greater than 0. Again, that means we can have our system decrease in entropy as long as the surroundings increase by a larger amount. So, entropy is not conserved. The entropy of the universe is always going up. The energy of the universe, E, is constant. But S of the universe, entropy, is always going up. So, note here that our second law states that the entropy of the universe must increase in a spontaneous process. And again, the entropy of our system can decrease if the entropy of our surroundings is increasing at least as much. It has to increase at least as much. Alright, so now let's look at molecular motions and energy. So, when NO gas reacts with O2 gas to form NO2, the total number of gas molecules is decreasing, because over here we start with 2 plus 1, so over there we have 3, and on this side we have 2. If we're decreasing the number of gas molecules, we're decreasing the disorder, because there we have 3 particles bouncing around, here we have 2. That means the entropy has to be going down. How can we then relate changes in entropy to changes at the molecular level? So, formation of our new NO bonds tie up more of our atoms in our products than were tied up in the reactants. And this means that the degrees of freedom associated with our atoms have changed. Degrees of freedom are how many ways our molecules can move or be arranged. So the greater the freedom of movement and degrees of freedom, the greater the entropy of our system. So if we've tied up some of our degrees of freedom, if we've reduced the degrees of freedom, then we've decreased the entropy. So individual molecules have degrees of freedom associated with various motions within the molecule. There are 3 atomic modes of motion. We have translational motion, which is the moving of a molecule from one point in space to another. So we've got some atoms bonded together. We can move it up and down, left and right, or forward and backward. So we've got 3 translational degrees of freedom. We've got some vibrational degrees of freedom, which is the shortening and lengthening of bonds within the molecule, or the bending of bonds within the molecule. And the last one is rotational motion, which is the spinning of a molecule about some axis. So if we have some molecule like this, we can spin it around this axis, we can spin it around this axis, or we can spin it around that axis. The degrees of freedom for various molecular shapes are shown here. And note that N here is the number of atoms within our molecule. So if we have a monoatomic molecule, that means it's really just a single atom, we have 3 translational modes. We can move it in 3 directions. There's no rotation because we just have a single atom, so rotating it means we still have the same thing. Vibration, there are no chemical bonds to vibrate around, so there's no vibrational modes, which means that a monoatomic molecule, which means just an atom, has just the 3 translational modes of degrees of freedom. With a linear molecule, we now have 2 atoms bonded to each other. So here we still can move it in 3 directions in space, so we still have the 3 translational modes. We'll always have 3 translational modes. And now with rotation, we can rotate about this axis, we can rotate about this axis, but if we try to rotate about this axis, we're not actually changing the molecule. We're just spinning along that bond, because again, it's linear, so we're just spinning along that central axis, and we still have the same molecule that we had before. It's not actually in a different orientation, which means we only have 2 rotational modes. So, now let's look at vibrational modes. All of the remaining degrees of freedom have to be vibrational modes. And we always have a total of 3 times however many atoms we have in the molecule. So if it's monoatomic, our total is 3. If it's diatomic, it's 3 times 2, so 6. So if we have 2 atoms in our linear molecule, like diatomic oxygen, O2, the only vibrational mode we can have is in and out synchronized. If we try to bend it, that's really just a rotation again. And so 3n minus 5, 3 times 2 minus 5 is 6 minus 5, which is 1. So in that case, we have one vibrational mode. If we have additional atoms involved, then we can have additional vibrational modes. If we have a nonlinear molecule, then again, the total number of degrees of freedom is still 3n, because it's 3 for each atom involved. But in this case now, the rotational, we have one additional axis around which we can rotate, and that means that now there's one fewer vibrational mode involved with our molecule. Energy is required to get a molecule to translate, vibrate, or rotate. And these forms of motion are ways in which the molecule can store energy. So if we put in a little bit of energy, we can get the molecule to rotate a little faster, or vibrate a little faster, or to translate faster, which means it just moves across in space faster. So the more energy stored in translation, vibration, and rotation, the greater the entropy of that atom. So we're going to talk a little bit about Boltzmann's equations and microstates. So this is statistical thermodynamics. So statistical thermodynamics is a field that uses statistics and probability to link the microscopic and macroscopic worlds. So the molecules and atoms that we see with the behavior that we see of bulk substances. So entropy can be connected to the behavior of atoms and molecules. Entropy is a property of a bulk substance, and with statistical thermodynamics we can then connect the properties of entropy with the properties of our atoms and molecules. So let's envision some microstate. This is a snapshot of the positions and speeds of all the molecules in a sample of a particular macroscopic state at a given point in time. So we've got some chunk of material, and all of the atoms and molecules in there are moving at some speed, they're moving in some directions, and we're looking at the states of all of those. That is one microstate. So let's consider a molecule of an ideal gas at some given temperature and volume. And in this case, a microstate is a single possible arrangement of the positions and kinetic energies of our gas molecules. So, but there are always going to be other snapshots available, other possible microstates. So each thermodynamic state then has some characteristic number of microstates that we're going to call capital W. And the Boltzmann equation is written here. That shows how our entropy, S, is related to W. So S is equal to K times natural log of W, where K here is Boltzmann's constant, which happens to be 1.38 times 10 to the minus 23 joules per Kelvin. And entropy is then a measure of how many microstates are associated with a particular macroscopic state. So any change in our system that then increases the number of microstates gives us a positive value of delta S, and vice versa. So if we lower the number of microstates available, then we have a negative value of delta S. So in general, the number of microstates will increase with an increase in volume, an increase in temperature, or an increase in the number of molecules, because any of these changes will increase the possible positions and energies of the molecules. Right? As we increase the volume, we have additional space in which our molecules can reside. If we increase the temperature, we've got additional energy around our molecules and are able to move faster. And thus we have a larger number of possible distributions of our molecules amongst all of their states. The last one was an increase in the number of molecules. If we stuff more molecules into a box, we have more possible states. And if we have one molecule in a box versus two, we're going to have more states when we have two molecules in the box. So that was entropy and the second law of thermodynamics.